second speaker in this session is going to be Ashesh Chattopadhyay from University of California, Santa Cruz. Sorry. And so he obtained his PhD from Rice and then worked at Xerox PARC and SRI for a while, after which he went back to academia.
Thank you so much. Okay, so I have an undue advantage that the three speakers before me talked almost everything about an introduction to AI-based modeling and climate modeling and all the challenges. So I can use up that time to talk about hopefully something else. So I'll focus on autoregressive models very similar to the kinds that were described by Chris and Laura. And then I'm going to transition into trying to distill out a theory of these autoregressive models that gives us some idea about these models' behavior, their spectral characteristics, and generally generally a diagnostic tool to talk about the quality of these models without running expensive evaluations at inference. So this work is done with a bunch of collaborators. I want to highlight the grad students involved in this collaboration. So we talked about ForecastNet. I know Pedram talked about it. Anima talked about it yesterday as well. One of the way these models are trained, and they're remarkable models in terms of how accurate they are by being trained just on data, right? There's no physics. And the key point to note here is that these are trained as autoregressive models, and I'm pointing it out because it looks at the state at time t and tries to predict the state at time t plus 6 hours, right? This is generally how these models are trained. Now, particularly for ForecastNet, it was actually trained based on 2 time steps. For example, you predicted 2 time steps ahead, very similar to how Laura trained her model as well. And the question was, well, do we need 2 time steps or not? Do we need some physical equations to constrain the loss functions? So these were some questions that were asked at that point as well. But generally, without any physics, just from reanalysis data, training on observation-derived real analysis data, these models turned out to be really, really remarkable in terms of how accurate they were, outperforming state-of-the-art gold standard physics-based model. Now, all these models have a general recipe to which how they're trained, right? You're trying to solve a partial differential equation that you've discretized into a bunch of nonlinear ODEs, and you're trying to predict the right-hand side with a large model that you're parameterizing with billions of parameters, depending on how much compute you have, right? And the loss function is one of the following. It's either the next time step minus what you predicted, next few time steps minus what you predicted, depending how much memory you can afford during the training process as well, right? So this raises a few questions. For example, there are some neural networks that are unstable, some that are stable, but maybe if you look at the statistics, they're a little unphysical. Some show faster error growth, some show smaller error growth, and those are sort of like philosophical problems as to is there like an optimal architecture to solving these problems. But then there are some more like real challenges. For example, which delta t makes more sense? Should I predict a day ahead, 2 days ahead, 10 days ahead? What about if I predict 30 days ahead? For a long-term emulation, that makes perfect sense. I'm running it for 100 years. But can I really train a model with a delta t of 30 days? So if you ask a numerical analyst, they would say smaller delta t is better. Why? Because 100 years of numerical analysis literature says so. But we don't quite have the same thing with machine learning models, right? So it would be nice to have a general theory of n, right, that determines the quality, stability, and so on. So what I'm going to do in the next few slides is that I'm going to take a model like this, very similar to Chris's model, slightly change the training strategy. And the reason I'm going to change this training strategy is so that I can do math a little easily in the later few slides. Build a stable emulator for the climate, apply it at scale, make sure that it works, it works reasonably to the first order as a climate model, and start doing some theoretical analysis with it. So the way I'm training this model is, again, something that Laura alluded to towards the end of her talk, is that let's model the tendencies. So again, I'm going to throw a big, deep neural network at it. Could be a vision transformer, could be a neural operator, could be something else. But instead of modeling the entire right-hand side, I'll model the tendencies, because that's what you kind of learn to do in numerical analysis. And then I'll have a smoothing kernel on top of it that looks like an integrator. So for example, for Euler, it's nothing, it's the identity matrix, except there's a delta t term that's multiplied to it. Now, if you're a machine learning practitioner, this looks awfully similar to that of a ResNet when h equals to identity, because ResNets are Euler ODEs, right? Except they're not quite, because the delta t is this extra term that's never really there in ResNets. And the generalization to that would be like an RK4 method or some other method. So that's really how we're going to train the model. Other than that, it's still the same. And then we're going to take observation-derived reanalysis data, just like Chris, look at 9 different levels, have CO2 as a forcing, prescribe SSTs, do things that you typically do in a climate model, and train an architecture. So in this case, the architecture is going to be SFNO with this change in training strategy. I promise you these were actually numbers and not hashtags, and this is xt to t plus delta t. Let's see how my other slides go in terms of math. The way so again, I'm trying to predict xt plus delta t from xt using some sort of a smoothing kernel by estimating the tendencies. The other small change that I make is that in the loss function, I have this extra term, which is calculating the difference between the spectral representation of the predicted or the estimated tendencies and the true tendencies. And the reason I do it is actually a bit of a tangent, but at the same time interesting, because there are these issues with these models where they either blur out the small scales or they overestimate the small scales. And this is one way to fix it. This is absolutely not the best way to fix it or the only way to fix it. But in the next slide, what I would show is that no matter what your model looks like, what n prime is, you would almost always have this bias in the small scales. And this is empirical evidence that you do. For example, all the AI weather models, if you compare, like, say, take any variable, look at their data in prediction. If you look at their spectrums, they're off from the black line. Black line is sort of the true spectrum. And this is not just error accumulation at day 10, but really, if you look at the first time step of prediction, this is literally what they were trained to do. You actually predict the state at about 1/4 of the true resolution. So you think you have a 25-kilometer model, but you really have a 100-kilometer model. But then these scales would either grow or these scales would die down. Depending on that, you're either going to blow up or you remain sort of stable but saturate to a more diffusive value, so blurring out and so on. And there are different ways to fix this. What I will take 5 minutes, or like maybe actually 2 minutes to talk about, is the fact that it would exist in almost all models. And the way to do that is I will take a simple one-layer neural network, derive spectral bias, and sort of pretend to do math induction on multiple layers. But the math here is pretty interesting, because if you take the affine transformation with a nonlinearity, it has this very simple spectral decomposition. And consider the nonlinearity to be tangent hyperbolic. In the next 2 clicks, the math will get nasty. So you can blissfully ignore the math and focus on the last 3 things that I will talk about, which is when you're trying to optimize this neural network, its parameters, you're trying to basically take the gradients of the loss function with respect to its parameters and move the parameters towards the gradient, along the gradient, right? So here are the parameters of the model, simple enough. This is what the first gradient looks like in spectral space. This is what the second gradient looks like in spectral space, and then del L, del W. You put all of them together, and this is the only bit that you need to focus on, is that the net gradient scales with 2 terms. The first term is how much of the small scales have you failed to capture at a particular epoch when you have presumably captured the large scales, and then times exponential of minus the absolute value of k. Now, if you think about it, the kind of systems that we're dealing with have spectrums that look like this. This is a decaying spectrum, which means that the power over here is about 5 orders of magnitude more than the power over here. So this number is a very small quantity. So this is very close to 0. This number for large values of k is another very small quantity. This is order 1. This is constant, doesn't change with k. So essentially, your gradient is 0. So at a particular epoch, while you have trained, you have 0 gradient, so you can't move, and you're stuck at your theta. So you'll always have this bias, depending how the spectrum looks like, and your loss function, it may be a little more, it may be a little less. And that is why we introduced that loss function that I talked to you about. It's a hacky way to all right. It's a hacky way to remove this spectral bias problem, and there are probably better ways to do that. So we put this together, and we gave a fancy name to our climate emulator. We called it Lucy. But it does exactly almost the same thing that sort of ACE does. And we have two versions of it, a very lightweight version where you can actually emulate the atmosphere with only a few variables without boundary conditions stably. And the reason we did that, we wanted to test whether the numerics work out or not, more than whether it's a useful climate emulator or not. And then we have a more comprehensive one where we do responses to forcings and so on. So this is the general idea behind Lucy. And I'll whisk through the next few results because this is more like convincing a climate scientist that we have a model that has a bunch of problems, but at the same time, it does some things well. Like it gets the 100-year mean climatology. If you don't have like CO2 as a forcing, it kind of mimics a simple, very low complexity climate model. And it gets the variability of large-scale waves correctly. It gets the time-space spectra of precipitation, which is sort of an important variability that we want to look at when we are building new climate models. Then we look at some of the other low-frequency variabilities, like persistent patterns in the atmosphere that you typically expect a climate model to get. And in this case, we do see that we get pretty good correspondence with what is, what are the SAM stands for southern annular mode, and NAM stands for northern annular mode. These are patterns you'd expect to capture. These look pretty well, even the average annual temperature range. Then we do some forcing experiments, exactly the way that Chris set it up, that we change the CO2. In this case, we put in the observed CO2, the actual historical CO2, and we see if the slope of the line that measures global temperature as a function of years, that matches with the observed slope or not. And roughly it does. So that's all right. But then really the actual test is the out of distribution tests where you keep increasing the CO2 and you see how the system responds. On the right-hand side, the larger CO2 responses look okay. Things get warmer. But on the left-hand side, we have a problem. The problem is that the poles react unphysically to this increase in CO2. So your low latitudes get warmer, but then your poles start to get cooler, which is not something that you'd expect. You'd expect polar amplification. So that's the problem. And then we investigate further. We look at sort of the vertical structure due to this non-stationarity. And we realize that our troposphere is OK in terms of the sort of climate change response, but then our stratosphere is terribly off in the sense that the temperature change is too high, which means that we have too high of a cooling in the stratosphere. Next, we do a few more tests, this time by perturbing the oceans, the prescribed SSTs. These ones are actually much more robust in the sense that they actually respond the way we would expect it to. So increasing SST gives us a net increase in the overall temperature. We don't get any unphysical responses over land, something that we struggled with for a while. And really, to get these right, it was more engineering than anything profound that we did in these models, making sure that you have the right, you don't have a huge mismatch between the land temperature and the surface ocean temperature. Then we investigate further into the stratosphere, which was a big problem in these emulators. And by the way, I'm doing all of this to establish the fact that this little change in the straining strategy does not impact the stability or the physical consistency of the model, because that's really what I'm trying to do to convince you. It is overall OK, but it has problems with the stratosphere. The temperature, the cooling of the stratospheric temperature is too high. Although if you actually look at the dynamics, and the way we show this is that we start off the Lucy simulation from 1980s and let it run for 23 years, and then look at like a 2013 SSW event. SSW stands for sudden stratospheric warmings. These are extreme events that models have hard time capturing. And we wanted to see if we get the overall structure correctly. And we do. We do get the overall structure correctly. We don't get the exact time. There's obviously a lag in this at the time when this SSW event happens, marked by a reversal of the flow, reversal of the temperature, and so on. But the overall dynamics is not too bad. So safe to say that we don't really have the stratosphere correctly, but at the same time, it's not completely, for a lack of a better word, garbage. So it's doing something. You can do other things with this atmosphere. So with this climate model, so you can start it off with a 0 atmosphere, as if there was no atmosphere in the Earth. It starts rotating this solar solar radiation, and it starts to build up an atmosphere, and that kind of converges to the climatology, something that you'd typically expect of a climate model. And you can play some other games, like you can hold the CO2 constant at 1980s, or change it by a bit, look at sort of what-if scenarios by starting off either with a 0 atmosphere or not. So overall, this emulator does reasonably well. It's stable, it's physically consistent, and this little change in the training strategy that we did, which we believe is a good thing to do, did not dramatically impact the performance of this model. So at this point, we can maybe then start to ask some of these theoretical questions, where we can think about, is there some theory that we can distill out from a model like this? A model that empirically shows good performance, shows stability, and so on. Is there some way to look at two different models that both apparently look good, but then talk about their respective qualities or stabilities and error propagation and so on? And in that process, maybe answer this question, is which delta type makes more sense? Should I train this model with multiple time steps, multi-step loss functions? That's typical in many models. Or should I train it with a single loss function? Do multi-step loss functions have an impact actually in terms of performance, and so on? So the way the theory should look like, and this is, it shouldn't be, is there a general theory? Can we have a general theory? And yes, my hope is that we would have a physical theory of error propagation, right? So if I say that I want to understand how a neural network behaves, it really means I want to understand how quickly a neural network goes bad as you autoregressively evolve it, which means I need a physical theory of the error propagation through these models, kind of similar to the physical theories of error propagation that we have about numerical solvers. So something very similar to that. And this theory should be independent of the inductive bias of n. It shouldn't change, the math shouldn't change between vision transformers or neural operators or CNNs or the other 1,000 other architectures, right? The only way the inductive bias should play a role is that if we do have a physical theory of error, the parameters of that model, the model of error, should be diagnosed from the inductive bias of the model. So these are the two things that we would focus on. And then, just like a faithful physical scientist, this model of error should hold up to empirical evidence that we obtain by training large-scale models on real systems, sort of neural scaling experiments, and so on. So how are we doing this? Well, the way we were going to do this is that we'll try to do linear stability analysis. So the recipe is follow a numerical analysis textbook until you hit a term that you can't say anything about or chew on, and then do a bunch of experiments to see how that term behaves. So that's the general recipe. So you have a true model, G, and you have your neural operator or your neural network, G tilde. This predicts, this is the true state. So your error at any time step t is G minus G tilde. Can't do anything with it. This is where our math stops. So what we're going to do is linearize this about ut. So now we can do a little bit more. As soon as we linearize this about the u truth, you have two terms appearing here. The first term is the generalization error, or the one time step error on which you've trained the model. So that's one of the errors. The other one is something that we see in numerical methods all the time. This is error amplification through the Jacobian. So if you're doing LSA, linear stability analysis for nonlinear systems, this term determines stability, at least locally. Now you can unroll this even further, and then this remains the same. This is generalization error at that time step, at the tth time step. And this one gets a little messy. It's the sum of the product of something projected onto these generalization errors. This is very hard to chew, so we'll get back to it a little later. But let's focus on this first. You have a generalization error between two great models coming from two great groups. This should be the same, roughly. This is the one that we have no control over. So let's look at how this works. For example, a model that you have trained as a direct step model. So you put the state in and you predict the state. This is what the Jacobian looks like. The eigenvalues of this Jacobian governs your stability. The only problem is you don't have a control over these eigenvalues. You can train a great model, it'll have great eigenvalues, but you don't have any local control over it. But if you just if you reparameterize it this way, then your Jacobian becomes identity plus delta t times something. And this, if you change your delta t, make it small enough, are going to give you eigenvalues that are the eigenvalues of the identity matrix, which is 1. So a simple experiment, 1D system, we can plot eigenvalues, eigenvectors. If you have H, which is like an RK4 kernel, you would have error propagation that is very small or very slow because all your eigenvalues are at 1. And because you couldn't really control the eigenvalues of G, you have one of them outside the unit circle. That is what pushes your error up. And this might make it unstable. Maybe it will do something later on. We don't really know. But locally, this is what happens because of the eigenvalues. So this gives us some diagnostic metric. These things you can calculate, and I'll talk a little bit more about it. You can calculate these pretty easily, even for large models, because of the structure of these Jacobians. So the way we decided to test this theory is use proof with Python. So we took 40 different models. We kept a simple 1D system, so we can plot eigenvalues, eigenvectors. We took 40 different models, different architectures, different loss functions, different integration kernels, and plotted it on the same plot. So anything with a smoothing kernel would have low error propagation. Anything without it, if you are not lucky enough to get an eigenvalue at that initial condition, which was by chance less than 1, it will blow up. It has to, because you have no control over it. And all these eigenvalues, there are about 1,000 of them, they cluster at the unit circle. This is not one model's eigenvalue. This is 40 models, 1,000 eigenvalues, all plotted on the same thing. It's because they cluster around with 10 power minus 6 as the standard deviation. Now, so this was empirical evidence that these eigenvalues have some, like we can probably determine at least the stability of the model locally. And as we go further, the quality of these models as well, because they tell us something about error propagation. And if your model starts with error propagation that looks like this, cannot, in the long run, be a better model than that. So let's look at this part of the equation one more time, because remember, our objective is to find a physical theory for error propagation. What does a physical theory mean? It means that I should be able to estimate a bunch of terms on the right-hand side using empirical evidence. Those will be the parameters of my theoretical model. Then I can predict error growth without running lots and lots of inferences of large trained neural network. So I take G, I write it out as the identity plus delta T structure, and now you basically have two terms here. One of the terms is the generalization error, and I'll jump the gun a little bit and tell you what these two terms do. This one is basically what takes you outside the distribution of your training set. So when you're running a model, sometimes you become out of distribution, right? You go unstable, or not, you just go crazy. This is the term that's responsible for it. This is like a forcing term. It's pushing, it's drifting you. If you're a dynamical systems person, then this Jacobian amplification is generally what we call error propagation. This is a bad term. This is like large eigenvalues are bad. So this is generally a bad term in dynamical systems analysis. In this context, because of the nature of the eigenvalues of H, remember, identity is removed from here. So these are all negative eigenvalues. So this is a negative trace matrix. It acts like a restoring force. So it jumps up, sometimes becomes stable because this acts as a restoring force. And you can show that this trace is negative, but I'll show you empirical evidence that these traces are negative. And then there are some higher order contributions that I will come back to in a bit. But now if I write out the right-hand side a little bit more, I'd find that ultimately your error at time step t plus delta t and t plus 2 delta t is going to be governed by this matrix, whose eigenvalues are basically 2 plus minus a very small quantity. So if this term has large eigenvalues, you're a bad model. If this term has small eigenvalues, you're a good model. So again, 40 different models. Let's put it on one plot and see if we can say that. These are all great models because they have small eigenvalues and small error growth. These have constraints. All of them have some smoothing kernel. But if you were to follow machine learning wisdom, these are the FNO type models, which generally is just a better inductive bias. We know that. We've done experiments. FNOs do really well. And they're here. So this theory reflects that. It reflects the fact that there's inductive bias that is captured in the eigenvalues. And as you move along this line, first of all, it follows a linear scaling law. And anything above here is going to be a slightly worse model than this. anything up here, which are sort of the direct step models, are the ones that are blowing up, and hence are out here because they're so large eigenvalues. The reason why I said that these are computable quantities generally, this Jacobian is a billion by billion matrix. So no eigenvalue decomposition algorithm works here. But incidentally, 5 minutes? Okay. Incidentally, these quantities are such that they can be estimated from the traces. I'll skip over this, but this holds true for implicit models as well. The theory of implicit numerical integration actually holds true. The stability theory kind of holds up for neural autoregressive models that are trained as implicit solvers as well. The eigenvalues are also diagnostic of spectral bias. For example, we know FNO has better spectral representation, and that is reflected again by the smaller, largest eigenvalue of these systems. And finally, this actually can be used as a regularization to better inform your loss function. What you can do is you can project your Jacobian onto the residue and then train a model which would give you basically lower error growth, more stability, and so on and so forth. So this little diagnostic can also be used as a regularization, as is the case for any or most diagnostic tools. I'll take the last 30 seconds to say that this error propagation model is a lot more interesting than just a bunch of equations. Because if you start expanding out the terms in this error, what you would see is that it alternates a forcing function, a restoring force, a nonlinear stiffness, a Duffing term. So it looks like a damped nonlinear oscillator as a function of delta t. So that tells us that there would be a minimum, a delta t that corresponds to a minimum error. So this graph kind of shows that you have trace, these are all trace negative quantities, and this sort of U-shaped curve tells us that, or is sort of validation that this energy function as a function of delta t should have a U-shaped nature. And that is determined by the structure of these 8Js, which are in this case the product of the Jacobians, the 3 tuples of the Jacobians. Anyway, so I'm out of time, so I'm going to leave my conclusions up here. What we wanted to do was come up with some semblance of a theory. It's not a great mathematical theory. It's better than let's run a model, see how it does, right? So something that closely investigates the physics that we are studying and trying to isolate problems as to whether they're an ML problem, data problem, or sort of a numerical problem, and so on. With that, I'll take questions.
Okay, thank you for the great talk. A short comment on the loss function you design, which is the L1 norm of the spectral. So my understanding is like what you really want to do is to add more weight add more emphasis on the small scale, the high frequency. So have you tried, like, for example, Sobolev norm or other type of norm, like add more emphasis on high frequency part and something? I think it's
yeah. Like any norm, as long as it's not the 2 norms squared, is going to emphasize the high frequencies, the high wave numbers in this case. Yeah. And you can also put a weighting term, which would even further emphasize it. So yeah, but none of them would mitigate this issue, right? Because you can't train up to machine precision. And if you have machine precision error at the small scales, the nature of turbulence is that it would eventually propagate back into your autoregressive model. So it's a hacky fix, but it's a fix nevertheless.
Because L1 of spectral is okay. You might, because L2 of spectral is just L2. It's similar and
exactly. So a little L2 squared.
Yeah.
Then Parseval's theorem says it will be the same, which is also, that is why we are doing this first of all on the tendency, and we are doing a 1 loss. But that is the insight why we are doing that, because L2 squared becomes L2 in physical space because of Parseval's.
Yeah. But the small scale is still like a high frequency part. So the main issue is like the magnitude of a high frequency is very small. And even if you are using L1, it's only alleviating a little bit, but not like fundamentally.
Right. So we only take the wave numbers after which we have not captured them.
Oh, I see.
Okay?
Oh, okay.
So it's an L1 between the wave numbers that we have not captured to the end of the wave numbers.
Okay, I see. Thank you very much.
So when we train what we do is, so after each
cheap factor training, we actually do a 5-year simulation and see how it works. And one of the things we learn from doing that is that as time goes on in your training of a auto-regressive model like this, your loss and your validation score both monotonically decrease with the amount of training, but at some point, often not too far into the training, the inference skill either gets asymptotes or often gets worse again. And I guess I think that is a little bit of a challenge to this approach, because I guess I would have expected with this approach that the kinds of errors that you could learn about from this would already be sort of visible in sort of either the validation losses or at least short-term forecasts, and yet we don't really see that kind of correlation.
So when we compute the validation loss, we only compute this term, right? We actually never look at this term. When you do multi-time step training, though, you look at, suppose you're doing multi-time step training up to 3 delta t's. Then you're looking at this expansion up to 3, like up to n equals 3. So when you're optimizing a loss function like that, you're directly manipulating the shape of h in this case. But when you're just looking at validation error for a single time step, we're never really looking at this quantity. And this quantity is a good quantity. Like it restores our error. It restores the model back into shape. And I feel like that's why perhaps stopping at a checkpoint and then looking at the long-term rollout as opposed to how much can we unroll during training and get insight from that. Maybe there'll be some insight that we had here. I should also tell you, all of this is like simple systems where I can plot eigenvalues and eigenvectors.
No,
What happens in ACE is a lot more complicated.
But that's the kind of level of complexity of system we care about.
That is true, yes.
In particular, we also find there's not much correlation between weather forecasts that are over, say, 20 or 50 rollout steps and climate skill. So
True.
Again, it suggests to me that you have to go beyond Taylor series kind of view of the whole.
Oh yeah, absolutely. I'm totally assuming that if your model, I'm looking at error close enough to the initial condition with the underlying assumption is that if your model goes really bad initially, it's unlikely that it is going to give you a very good climate.
Okay. Maybe time for one more question. Yeah.
So you might have said this in a different way in the talk, but were you able to use this analysis to essentially predict which models are unstable currently, and say for a model that we know from the literature is unstable in long rollouts, can you kind of say if it has a 6-hour time step today, have you been able to say like it should have a 10-second time step or whatever to make it actually stable in rollouts?
Right. Let me clarify that. Like, absolutely no. Those are too big models for me to be able to compute, do this analysis on. What we did was trained our own bunch, made some of these models unstable, made some of these models stable, and retrogressed and saw and sort of validated whether the theory is able to predict it correctly or not, which it does. Very small systems. So we looked at 1D systems. Then there's a big data set called the Well data set that Flatiron had. So we trained a bunch of models on that and was able to get that. But in terms of large AI weather models, no, absolutely. No, we haven't. We don't even know how much of this will eventually scale there. So.
All right. Okay, so that's the biggest.
Thank you.